Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 39, Synchronous Counters Design with D Flip-Flops of Chapter 7, Counters and Registers of the course Digital Logic Design for Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite free references in digital logic design, however, there are many books available. Chapter 7 contents include digital counters, ripple counters, binary ripple down counters, binary ripple up down counters, and other ripple counters. We covered all of these topics in the previous lecture, lecture number 38. Today we will cover the synchronous counters and design of synchronous counters using D flip-flops. Synchronous counters characteristics. All the flip-flops are clocked at the same time, simultaneously or synchronously by the input clock pulses. So, unlike the synchronous counters, here all flip-flops are clocked by the same clock pulses. The carry propagation delay of ripple counters may be reduced considerably. Repetition rate is limited by the delay of any one flip-flop plus the propagation times of any control gates required. Therefore, synchronous counters are much faster than ripple counters. Another advantage of the synchronous counter is that no decoding spikes appear at the output, since all flip-flops change state at the same time, simultaneously. For these reasons, synchronous counters are the designer's choice for all high-frequency applications and high-speed digital computers. When you work in gigahertz, synchronous counters is a must choice. Synchronous counters versatility. A synchronous counter can be one of many of the following counters. A binary up counter, such as a mode 8 or modulus 8, mode 16, etc. Could be a binary down counter, such as mode 8, mode 16, etc. A divide by n counter for any integer n where n is not a multiple of 2, such as a decade counter or mode 10, mode 6, mode 7, or mode 12 counter. A non-binary sequence counter for application-specific counters such as all-add sequence counter, or all-even sequence counter, array code counter, or a counter with specific sequence such as 2, 4, 7, 6 to 0. So any counter, actually with any sequence, can be designed. Also, we can design an up-down counter. Now, for all these counters, for any type of counter, if it is synchronous, we can design it, and there's a simple procedure to do so. This slide is extremely important. Is the design procedure for synchronous counter. Okay? Step number 1. I would like to determine the number of flip-flops n required to support the counting sequence. The counting sequence highest number n. The number of flip-flops n is the smallest number for which 2 to the power n greater than n. So if we have 8 states, we need 3 flip-flops. If we have up to 16 states, we need 4 flip-flops. As simple as this. Okay. 2. I will choose the type of flip-flop to be used. A specific type of flip-flop may be required in the problem design statement. A more complicated design problem, 2 or more different types of flip-flop may be used in one counter design. So here we could use a D-type flip-flop, or we could use a T-type flip-flop, or SR flip-flop, or JK flip-flop. Now, the type of flip-flop depends on the availability of the flip-flop, the cost of the flip-flop. You know, SL flip-flop is the cheapest, or SL latches. So often they are chosen because they're the price. However, we have to design them. We have to design to find the excitation input for every flip-flop, namely SA, RA, SB, RB, and so on and so forth. Or TA, TB, TC for T, triggered flip-flop, or JK, flip-flops. So indeed, where the input excitation has to be driven. It is useful but necessary to construct a state transition graph that include all states that are not part of the counting sequence can go to the reset state as 0 or any desired state in the counting sequence, or their next state can be assigned as don't care. So often states are not used. We prefer to assign them as don't care for the simplest hardware required to design the counter. So if you are looking for the most frugal hardware, I will use the states, the next state for unused state as do not care. I don't care where to go. Derive the state transition table, tabulating the present state in a binary sequence and the next state, then the excitation input of the chosen flip-flop. So if we are choosing the flip-flop, what we need only the next states. Because of the next state, A plus B plus C plus, DA will be A plus, DB will be B plus, and DC will be B, DC will be C plus. Okay, now once I have the excitation input of the chosen flip-flop and the present state table, flip-flop excitation input can be determined from the chosen flip-flop's characteristic equation or from excitation requirement table. We covered those with any specific flip-flop. Go to those lectures to find the excitation requirement table. Use K-maps to find a combinational logic function for each flip-flop excitation inputs. We need those J's and those K's, or the T's, or the D's, or the S's, and the R's for the S of the flip-flop. Since once we have all these data, okay, we use K-maps to find the combinational logic function for each flip-flop excitation input, find a combinational logic function for the present output, if any, and draw the logic diagram design counter. Actually, this design procedure method is so beautiful that it could be used for any sequential network. For any sequential network, we can use it and utilize it, okay, as we will see in the future, in the near future. So let's take an example to design a mode 8 synchronous up counter using D flip-flops, because this lecture talks about D flip-flops. So mode 8 up counter will count from 0, 0, 0 to 1, 1, 1. So initially we have state 0, 0, 0 to 0, 0, 1 to 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and back to 0, 0. If you make a state representation, or we call it state assignment, we assign S0 to 0, 0, 0. This is S1 to 0, 0, 1, which is equivalent to the binary number, S7 to 1, 1, 1. So we'll get this graph. So this is with binary state assignment. We did binary state assignment. Okay. Now with this, definitely will remain. This is if X is 1, if you remember. Okay, when there's a clock pulse, there's a transition. If there's no clock pulse, we will remain. So if X is 0, we will remain in this state until X is 1. And those are not shown here. Now from this, we can generate the state table for mode 8 counter as shown here. I have the present state, which is ABC. A is the most significant bit, and C is the least significant bit. And the next state, which is A plus, B plus, and C plus, and this is assumed for X is 1, okay? Because X is 0 really has no importance or change in the design at all, so why we consider it? Okay, it's giving me different states here because just it's a clock pulse. It's not a real input to the counter, okay? So if I am in state 0, 0, 0, the next state will be 0, 0, 1 with the clock pulse. If I am in 0, 0, 1, the next state will be 0, 1, 0. Until 1, 1, 1, the next state will be 0, 0, 0. So this is a binary counter. It means we are counting in binary sequence, which is equivalent to the decimal sequence 0 to 7. 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 and back to 0. Now, once we have the state table, okay, we have state graph and the state table, we can go and draw the K-map of A plus, B plus, and C plus. So what we have, A, B, C, and look, the A plus is 0, 0, 0, 1, 1, 1, 1, 1, 0. Okay, and this is how we A plus we map it. 0, 0, we jump 0, 1, 1, 1, we jump 0. So we have the K-map for A plus. The same thing with B plus. B plus is 0, 1, 1, 0, 0, 1, 1, 0. 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0. So the same thing with C plus. 1, 0, 1, 0. It is C plus 1, 0, 1, 0, 1, 0, 1, 0. And you see it here. 1, 0, 1, 0, 1, 0, 1, 0. So once I have C plus map, A plus map, B plus map, and C plus map, we can minimize those functions. We can get A plus, and A plus will be AB prime, AC prime, A prime, BC. But we know actually from the characteristic equation, D is equal to Q plus. Here, it's DA will be A plus, DB will be B plus, and DC will be C plus. Okay, for instance, DC will be C prime. It is 4, we have a set of 4, and the 1 will cancel with the 0 horizontally. Vertically, we have the 0 will cancel with the 1 for the B, so I have only C prime. So C plus will be C prime, which is DC. So once we have DA, DB, DC, we can draw the diagram of my counter. So the mode 8 synchronous up counter will look like this. We have C prime is equal to DC. C prime short circuit is equal to DC. Right? We have B exclusive or C for DB. B output, okay, the B output here, take it to the exclusive or with C, the C, take it with C, the output will go to DB. And DA will be a combination of AB prime, AC prime, A prime, BC. So we used 3 AND gate and 1 3 input OR gate to do the job, as you can see here. But we use all NAND gate structure. Okay. With this, actually, we designed the mode 8 synchronous up counter fully. And now the next slide talk about the non-binary sequence counters. And we talked about this in some application. The sequence of states of a counter is not a straight binary order, such as all add sequence counters or even sequence counters, gray code counter, or any other sequence. It depends. We will design a counter which could count 0 to 3 to 7 to 4 to 6 and back to 0. So we have 3 state missing. Okay? We have 0 to 3, 1 to 2, 1 is missing. 2 is used here. No, this is 4. I do apologize. So 1 and 2 is missing. And we have 0, 0, 0, 0, 1, 1. 0, 1, 0 is missing. 1, 1, 1. We have 110, 101 is missing. 101 is missing. And 001 is missing. So 010 and is missing as well. So the count will be 0 to 3 to 7 to 4 to 6 and back to 0. 1, 2, 3, 4, 5. 5 states, and we have 3 missing states, or unused state. Now with this, once we know the count, we can draw the state graph and the state table. So we have 0, 0, 0. If I have a clock, I will go to 0, 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, back to 0, 0, 0. So the present state will be ABC. We call them A is the most significant bit. 0, 0, this is will change 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. 0, 0, 1, 1, 0, 0, 1, 1. We have them in the binary sequence from 0, 0, 0 to 1, 1, 1. Now, what's the next state for 0, 0, 0? Is 0, 1, 1. What's the next state for 0, 1, 1? We say 0, 1, 1 is not used. The next state is don't cares. What's the next state of 0, 1, 0? Is also don't care. What's the next state of 1, 0, 1? Also don't cares because it's not used. What's the next state of 0, 1, 1? If I am 0, 1, 1, next state is 1, 1, 1. 1, 1, 1. So A plus B plus C plus will be 1, 1. If I am in state 1, 0, 0, 1, 0, 0. Where is 1, 0, 0? It's right here. What's the next state is 1, 1, 0. 1, 0, 0, 1, 1, 0. If I am state 1, 0, 1, we say don't care. Don't cares. If I'm state in 1, 1, 0, 1, 1, 0, the next state will be 0, 0, 0. If I'm state in 1, 1, 1, the next state in 1, 0, 0. The next state in 1, 0, 0. See, the state graph is very helpful. Although we can do it without it, but it's very helpful to fill out the state table. So once I have a state table, I will go to K-map, and I will have K-map for A plus, B plus, and C plus. And the K-map will look like this. The A plus K-map will look as 0, don't care, 1, 1, don't care, 0, 1. Okay? So we read it. 0, don't care, 1, 1, don't care, 0, 1. The same thing with B plus. The same thing with C plus. We need K-map for each. Okay, so for instance, C plus will give me a set of 4. We use 1, don't care. And this will enable me to get A prime. So we define A prime. We define A plus, B plus, and C plus as a function of A, B, C. And this is what we get. We get dA is equals to A plus, which is equals to C or AB prime. But with NAND gates is equal to C prime, AB prime, all prime. dB will be P plus, which is A prime or B prime or AB prime. It's one NAND gate. And DC, which is C plus, which is A prime. A prime. So we got actually the Boolean function, and those are the excitation input for the flip-flop. Now we can draw really the counter. For instance, DC is A prime. See, A prime is here. We did not put the line to avoid intersections. So this output here from A prime, you connect it to DC. AB, A NAND B, A, which is here, and B, which is right here. A NAND B, we take it to DB. And DA will be C prime, NAND AB prime, NAND, okay, AB prime, and will be DA. So we have the counter. We will draw the counter, and this would be the end, and this is the complete solution of the problem. We designed synchronous counter with non-binary sequence, and this is really a great thing to do. Let's look at analysis procedure. Now, if I am given a counter, a specific counter, and I've been asked to identify this counter. Is it a mode 5, 6, mode 8, mode 16, mode 17? And I would like also to know the real sequence, the real count sequence of the counter. So what we do really the opposite to the design. From the counter logic diagram, from the given diagram, I will find the logic functions of the excitation input of each and all flip-flops. Use the characteristic equation of each flip-flop to determine the corresponding next state logic function, which is A plus B plus C plus. So we map the next state logic function into K-map, map the logic function of the output, if any. There's output coming from the counter. We combine all K-maps from the counter state transition table. The table must be tabulate the present state in binary sequence and the corresponding next state and the output, if any. We use the binary state assignment and draw the state transition graph. So we'll identify and we will analyze the counter fully. So the analysis procedure is really, and this analysis procedure works with any sequential, with any synchronous sequential network as well. Okay, let's take an example and see how the analysis will work. We are given this counter. So we define A plus, B plus, and C plus to be C or AB prime, A prime or B prime, and C plus to be A prime. Now, and this is, so from this graph, from the logic diagram of the counter, we obtain the logic functions. We call them A plus, B plus, C plus. So we find A plus, B plus, and C plus from the characteristic equation of the D flip-flop because we know DA, DB, DC, and we know A plus is equals to DA, B plus is equals to DB, and C plus is equal to DC. Once we have those equations, we will map them into K-map. So we will map the equation A plus into ABC. By mapping them, we get the following equation, the following K-map, A plus. How did we get this? We know that A plus is C or AB prime. C, those 4 cells represent C when we map because this is C. This is C, okay? And since those will cancel out, and 0 will cancel out with 1 for the B, so those cells will represent C. And the second product term we have in A plus AB prime. Where is A and where is B prime? We have A is here, okay, so this is A, and B prime, we have B prime is here because I have 0 and 0, and 0 will cancel with the 1. So those two cells B prime, and this vertical line is all for A. So those two, okay, will be 1, 1. Okay, so those actually, so I will have 1, 1, 1, 1, and 1 for A plus, A plus. The same thing with B plus. I will map B plus. C plus is very simple because C plus, which is DC, is equal to A prime. And A prime is simply here. So I have 1, 1, 1, 1. This is A prime right here when it is 0, right? So 1, 1, 1, 1. Well, we map A prime for me. Everything will cancel horizontally and I have only A prime. Okay, so once we mapped A plus, B plus, and C plus, I will go and generate the state table. Let me show you how to do this. This is very simple. I have the present state AB plus, ABC, and A plus, B plus, C plus. I go to the K-map and read minterm by minterm, starting with 0, 1, 0, 1. Okay? Then 1, 1, 0, 1. I write them here. 0, 1, 0, 1, 1, 1, 0, 1. You see? And this will be the A plus. Next to it, I will put the B plus. The B plus again will come from 1, 1, 1, 1, 1, 1, 0, 0. So on the table will become 1, 1, 1, 1, 1, 1, 0, 0. Then we read the C plus. 11110000, and this will be 11110000. Now I can map. If I am in state 000 without state assignment, okay, I will go to 011. If I am in state 011, I will go to 111. If I'm in state in 111, I will go to 100. If I'm in state in 100, I will go to 110. If I'm in state in 110, I will go to 000. I will close the loop. How about those missing states? 010, 010 will take me to 011. So if the counter starts at 010, incidentally, I will go to 011, then I will continue counting in the order that I designed, or has been designed, which is this count. Okay, so those are the unused states. 001, if I start at 001, I will go to 111. If I start at 101, which is this state, I will go to 110. So the counter will not generate an error because there is no other closed loop. The only closed loop is the loop which starts with 000 to 011, 111. If those three states generate a loop somehow, so the counter will stay in undesirable loop, and this design will be not a good design. So we have to redesign it to avoid the problem. So sometimes, actually, the design may be really normal, an error in the design, and the design will not work right if we have another cycle, okay, for the counter. But this case is not. The counter is fine and works perfectly correct. This is the end of this lecture. I would like to thank you so much. Please subscribe by clicking on the blue circle, and hopefully see you very soon in the next lecture. Sincerely, Dr. Hassan.